Okay, I'd like to welcome everybody to Low C3 2020. I hope you've enjoyed all the presentations you've viewed so far. My name is Robert Tyler Hughes. I'm a graduate research assistant at Tennessee Tech University. I'm going to be going over the preliminary investigation of higher grade 100 slag substitutions in a Tennessee bridge deck concrete mixture. And here's a list of all the authors responsible for this project. Do a little intro and significance here. So since the production of Portland cement causes about 4% of the world's CO2 emissions, anytime we can decrease the amount of PC used in our concrete mixes, we're going to jump at that opportunity. And by incorporating supplementary cementitious materials, SCMs, like grade 100 ground granulated blast furnace slag, which I will definitely refer to as GGBFS, these emissions can be reduced dramatically and conserve natural resources. Now, the use of GGBFS not only has an environmental impact, but can also help save money due to the high cost of PC, because this slag is actually less expensive than PC. So by incorporating this slag in concrete, the cost of storing the byproducts in a waste landfill is reduced, which is in turn beneficial to the environment as well. And the incorporation of SCMs also has a very significant impact on hardened concrete properties that you'll see later. So the Slag Cement Association recommends GGBFS substitutions levels of 25 to 65% to lower concrete permeability. So since knowing this, the research team decided to start with a 35% substitution, since it's the highest substitution currently allowed by TDOT Class D concrete specs. The main objective of this research is to compare the performance of a TDOT Class D concrete without an SCM, comparing to mixtures containing GGBFS at different substitution levels for Portland cement. The plastic properties that were established to maintain consistency of the workability throughout all these mixes. Now, this was performed in order to keep all the mixes in compliance with TDOT Class D specs. Now, the hardened property tests include surface resistivity, SR, compressive strength, and absorption. So first, let's look at the different mixes that we used for this. Our control slag, or our control, is a 0% slag, so 620 pounds per cubic yard, which is the TDOT minimum. And you'll see all the TDOT requirements, I think, in 2 slides. So, but you'll notice that each of these cells will add up to 620 because of the substitution factor. And this is our 35, 40, and 45% substitution. 50, 55, 60, and 65. So 8 mixes altogether. And here we see some of the TDOT requirements. This is the minimum that I was speaking of a minute ago for the 620 pounds per cubic yard. Now, our water cement ratio, we use what we found to be an optimum ratio of 0.37. We keep that a little less than the 0.4 max that TDOT requires. Same thing with a percent fine aggregate by total volume, aggregate volume is 38, a little lower than our 44 max, but that we have discovered that is a pretty optimal percent for us. And like I said earlier, anything above a 35% slag substitution for Class D concrete is out of spec, so we have 6 batches that are out of spec for TDOT to examine how we could go beyond it. I'll get into some of our testing protocols. The 3 tests we use, like I said, compressive strength, SR, and absorption after boiling. A compressive strength was tested at 28 and 56 days. We had 3 4x8 cylinders tested at those intervals in accordance to AASHTO T22. SR is a lot more, we tested that a lot more because that is our judgment of permeability of the concrete. So we do 3 cylinders at 7, 14, 21, 28, 42, and 56 days, which is okay because it is a non-destructive test method. Like I said, it'll measure the permeability of the concrete. And absorption after boiling, a measure of porosity. We do that at the end of the cycle at 56 days. We use 3 of our 3x6 cylinders for that. Okay, so the acceptable range was determined by first multiplying the test method multi-laboratory COV by a factor from ASTM C670 for the number of results. Then the product was multiplied by the mean result to obtain the allowable range. And when available, we use the multi-lab precision factor because AASHTO T22 states that preparation of cylinders by different operators would probably increase the variation above multi-lab precision criteria. Now, all of our hardened property test results met the acceptable precision criteria except the 0% substitution and the 40% substitution, and that'll be indicated in a future slide. And also, there is no precision criteria available for hardened concrete absorption after boiling, so there is no comparison there. So we'll look at our compressive strength results. Now, this is what I was saying when our 0% and 40% did not meet the allowable range from ASTM C607. But you can see our mean compressive strength, not linearly necessarily, but does increase with higher substitutions. And we're not extremely disheartened about the non-linearity because this isn't really the main objective of the research. It is definitely an excellent byproduct of what we're trying to reach. We're trying to get to higher or lower permeability, but an increase in compressive strength is definitely never a bad thing. So, like I said, the 0 and 40 are out of their allowable ranges, but an acceptable byproduct from what we're trying to do. Now, our absorption and voids in hardened concrete. Here's our boilers and the oven that we use. And this looks like a lot of numbers, and it is because there were 6 batches of each variable. And what I would point out the most is our means here, and kind of like compressive strength, a little bit more important than that. Porosity, other studies can say that the use of SEMs doesn't necessarily decrease porosity, but it will decrease permeability. So at a very high substitution, we did see a decrease in porosity, a decrease in absorption after boiling, which is good, but definitely, or again, not the exact results we're looking for. So it is good to see that it is acting as it should, but extremely high substitutions. Now our SR results, which, like I said, is the measurement of permeability. And here we have a column for each, the mean SR and the range. And our SR, we use these Resipod ProSecs, the 38 millimeter, I believe, that puts a charge from the external probes through the 4x8 cylinder, and the middle probes will measure the potential in between it. So a higher SR value is better because that points to more surface resistivity and less permeability. So here, obviously, we're very good with ranges once at a control level, and our ranges get a little higher at the higher substitution levels. But you'll definitely see an increase in 56-day SR throughout each substitution. Let me go over to the 50 to 65%. And you'll see here at 60%, our mean is 114.9. And past that, at our 65, it did decrease. So we'll talk about that a little bit more in the results section and conclusion. But we did peak at 60%. So we'll look at the compressive analysis, like a statistical analysis of our compressive strength results. So it was not performed because both the grade 100 GGBFS and the 100% PC mix met TDOT 604.03 standard for compressive strength easily. And again, since the focus of this research is about the chloride ion ingress rate and permeability, it was only desired to get each mix to at least meet the minimum allowable TDOT specs for compressive strength. So the results showed that each concrete mix surpassed this 4,000 PSI minimum at 28 days of curing. Statistical analysis of SR. So each grade 100 GGBFS concrete mix was determined to the was compared to the control mix, 100% PC, using a two-sample t-test to determine which mixture had the highest electrical resistance or surface resistivity. The results showed that the grade 100 GGBFS at all substitution rates were significantly different and superior than the control 100% PC at all testing intervals. So lower permeability should slow the process of chloride ion ingress into bridge decks, which will therefore extend the service life of the bridge deck. Now, the green shaded cells in the next slide indicate a statistically significant difference, with the slag mix being superior to the 100% PC and SR. You can see that here. Every scenario at every testing date is significantly different and superior. And this is a graphical representation of our SR that I was talking about earlier. You can see here our peak at 60%. So this points to, for the probable use of a TDOT Class D mix, maybe a 65% is not the best idea. Anything 60 and less is more optimal for permeability reasons. And this is graphically, well, we have some bar charts here. You'll see that our 60% substitution was higher in SR than at every interval except for 7-day, which was 55. But every time we're glad to see that that substitution was higher for every testing date. So a statistical analysis of absorption after boiling. And the results table showed that the 56-day absorption after boiling results are below the 5%, which is the upper limit for high performance concrete. Therefore, it's important to point out that the absorption after boiling results for all mixtures were very good. Each grade 100 GGBFS mix was compared to the control by using a two-sample t-test to determine which mix had the lower absorption after boiling. The following table shows how each grade 100 GGBFS mix compared to the control at 56 days. The absorption results coincide with other studies that the use of SCMs may decrease permeability, but not necessarily porosity, like I was saying earlier. So this explains why most of the absorption results are either inferior or not statistically different. So get into some conclusions here. Based on our testing of one sample of grade 100 GGBFS, we can say that the slag we used, the GGBFS, although it was higher than TDOT allowable substitution, it was able to outperform the 100% PC while achieving the required plastic properties set forth by TDOT 604.03. And the increased substitution levels increased the strength and lower permeability at all ages, even though strength was a byproduct of what we were trying to achieve in lower permeability. The absorption after boiling results coincide with other studies that SCMs may decrease permeability, but not necessarily porosity, and that the lower permeability generated from GGBFS should increase the service life of bridge deck PCCs significantly if TDOT would allow higher allowable GGBFS substitution rates in their Class D specs. So our acknowledgments, we definitely want to thank Megan Dangle of Lafarge for the donation of the slag, Denny Lim from BASF for his constant donations of chemical admixtures. We'd also appreciate the procurement provided by the Tennessee Concrete Association. I'd also like to thank Mark Davis for his patience and skill in fabrication, maintenance, and repair of the equipment. We also appreciate the financial support of the Tennessee Tech Department of Civil and Environmental Engineering, and also would like to thank the administrative, financial, and information technology support provided by the Tennessee Tech Center for Energy Systems Research. I look forward to your questions, and thank you all for listening in.